Hello everyone. Today we are going to analyze this frame using strain energy method. In this frame, the columns A, B and C, D having the same height as 4 meter. The beam BC has the length of 6 meter. In the columns there is no load. In the beam BC there is a concentrated load 78 kilonewton. It acts at a distance of 2 meter from B. In the points A and D there are hinged supports. In this frame the number of unknown reactions and moments are 4. There are 2 vertical reactions and 2 horizontal reactions. The available equilibrium equations are 3. So the degree of static indeterminacy will be 4 minus 3. So it will be 1. Let us keep the horizontal reaction at D, HD as the redundant. To find the vertical reaction VA, let us take a moment about D. In this case, we have to follow right hand side rule. VA is acting in the clockwise direction so that it will be positive and the distance is 6. So 6 VA. This load is acting in the anti-clockwise direction so that it will be negative and the distance is 4. For VA, we will get 52. Using this rule, we can find VD. We know that in this frame, there is no horizontal load, so the values of HD and HA will be same, only the directions will be different. Let us assume that HD is acting towards the right side, so HA should be acting towards the left side. And we know that the values of HD and HA will be same. So instead of HA, we can apply HD. We know the formula for the strain energy due to bending. In this frame, we have to make sections. Let us keep this point as E. There are 4 different parts A, B, BE, EC and CD. So we have to make 4 sections, one in AB, one in BE, one in EC and one in CD. You can see that I have made 4 sections. This section at a distance of x from A, this section at a distance of x from B, this section at a distance of x from C, and this section at a distance of x from D. Since there are 4 sections, we have to split this formula into 4 parts. This is for this section, this is for this section, this is for this section, and this is for this section. Here the limit is 0 to 4. Here the limit is 0 to 2. Here the limit is 0 to 4. And here the limit is 0 to 4. To find the moments in these 2 sections, we can use the right hand side rule. Let us find M1. Up to this section, we have HD and VA. For VA, there is no perpendicular distance, so we should not consider this. HD is acting in the clockwise direction, so that it will be positive and the distance is x. So HD into x. Then we have to partially differentiate M1 with respect to HD. For HD, it will be 1. 1 into x, it will be x. Now let us find M2. Up to this section, we have HD and VA. HD is acting in the clockwise direction so that it will be positive and the distance is 4. So for HD, VA is acting in the clockwise direction so that it will be positive and the distance is x. So 52x. Let us partially differentiate M2 with respect to HD. For HD it will be 1. In this term there is no HD, so the differentiation will be 0. 4 into 1 it will be 4. To find the moments about these two sections, we can use the left-hand side rule. Let us find M3. Up to this section, we have VED and HD. For VED, there is no perpendicular distance, so we should not consider VED. HD is acting in the anticlockwise direction, so that it will be positive and the distance is x. So HD into x. Let us partially differentiate M3 with respect to HD. For HD it will be 1. 1 into x it will be x. Let us find M4. HD is acting in the clockwise direction, so that it will be positive and the distance is 4. So for HD, VED is acting in the anticlockwise direction, so it is also positive and the distance is x. We can partially differentiate M4 with respect to HD. For HD it will be 1. Here there is no HD, so the differentiation will be 0. 1 into 4 it will be 4. When we partially differentiate the strain energy U with respect to HD, we will get the horizontal deflection at D, which is 0. Let us partially differentiate U with respect to HD. When we partially differentiate these with respect to HD, we will get these. Then we can eliminate 2. 1 upon EI is common. We can take it outside, and on the other side 0 into EI, it will be 0, so that we will get this. In this equation, let us apply the moments and the partial differentiations. We can multiply these two, we will get this, and we can multiply these two, we will get this, and we can multiply these two and these two, we will get this. Then after integrating and simplifying, we will get HD. For HD, we will get minus 9. We will get a negative value. That means our assumption is incorrect. We assumed that HD would be acting towards the right side, but actually it is acting towards the left side. We have found HD. It is acting towards the left side. In this frame, there is no horizontal load, so the values of HD and HA will be same, but the directions will be different. HD is acting towards the left side, so HA should be acting towards the right side. Now we can draw the free body diagram. Using that, we can find the shear force values. These are the shear force values in the column AB. These are the shear force values in the beam BC. These are the shear force values in the column CD. This is the shear force diagram. Using the right hand side rule, we can find the moments at A, B and E. Then using the left hand side rule, we can find the moments at D and C. This is the bending moment diagram. Suppose if we draw the bending moment diagram in the opposite side, that is called the bending moment diagram on the tension side. This is the bending moment diagram by superposition method. Now we are going to end this session. Thank you for watching this video.